these surfaces are oxide anions, and then titanium would be 4+, which is fine. Another is hydroxide anions, and then we would have titanium 3 and titanium 4, still okay. And then also with fluoride, okay? And then this would give titanium 3 and titanium 4. So termination does not only give a right justification or approach for the valence or the formal oxidation state of the metal, in this case titanium, but also coordination of the metal atoms in the surface makes much more sense. Now, this is the founding paper of mxenes with, you can see the delamination of the precursors. The precursors, in an equally original way, they are called max phase. You know M and X, what it means. Then A in the middle, max. A is for aluminium or other elements from group A. So could be also silicon, germanium, and other elements that were discovered in the 60s in the group of Barsoum, but then delaminated only in the late 90s, and then more recently fully characterized in 2011. And you can see the family here that as transition metals, you have a number of elements, titanium, vanadium, and so on, carbon and nitrogen, so metal carbides or metal nitrides, and then termination, as I told you before, oxygen, hydroxide, fluoride, chloride, bromide. And then this was 2011. Now in 2023, little has changed in terms of chemical composition that you can see in the bottom right. So now formally we can, it is better to introduce Tx as termination, and X means we don't know how many units of terminations are there. Now, according to this, they could also be called mxenes rather than mxenes, but this is the right way to understand the material properties. Then only scandium has been added from the original list of atoms that could be making part of mxenes. But then in the terms of surface group, there is a large list of more terminations that have been more recently introduced, sulfur, selenium, tellurium, and so on. And then the number of variants for the synthesis is really large, and this affects the number of layers that are delaminated and also the morphology of layers. So these are really very tunable materials, and the family is large not only because of the chemical composition, but also because of the morphology and the properties of the termination atoms. Now, properties of mxenes are quite important. So I can tell you from my humble opinion, mxenes are not a hype. And in particular, one thing that is important is that they are electric conductors. Okay, so even in this paper that I selected here in 2020, they are even superconductors at low temperature. So in the upper left, we can see that the original max phase with aluminium, niobium, aluminium carbide is not superconducted, but then when the material is delaminated, and therefore we have the mxene, in this case aluminium is removed, and then the termination is chloride, then the material becomes superconductor. And then also depending on which groups we put in the surface, so here in this work, not only oxygens, sulfur, selenium, tellurium, and a few others, depending on what we put in the surface, the superconducting properties change, and they are somehow tunable. Another one that I selected is mxenes can also be used for radio frequency antennas, and normally made by metals, but then apart from the electric conductivity of mxenes, which is good for this, then the property that they can be easily delaminated, and they are also flexible. Therefore, they introduce interesting properties for this kind of devices. But now mxenes are catalysts is not so straightforward that they are good catalysts, and this is something that still needs abundant research. There are many groups working on that. So I selected from a few work just to introduce you what I think is the, let's say, promising way in which mxenes can be tuned as perhaps good catalyst. This is the case of mxene in molybdenum carbide, mxene, in which the termination is oxygen anions, and then copper nanoparticles are introduced in the material for the hydrogenation of carbon dioxide to methanol. Now, this is a well-known reaction. There are state-of-the-art catalysts using materials, zirconium oxide, zinc oxide, different supports, and so on. But copper is the key, and then copper plus, if this balanced oxidation state is stabilized, then this is the active, important part of the active site for this reaction. So it seems that in the preparation, they were authors of this study made, depending on the missing atoms in the surface that can be worked out depending on the delamination process. Then the copper nanoparticles interact with molybdenum atoms and even with missing molybdenum atoms, and this also allows to stabilize copper +1, and therefore, according to the computational study that we see below, the activation barriers of all these steps of the reactions are not too high, and this could be good catalyst. I mean, probably not competitive with the state of the art, but the idea behind is how to make mxenes interact with external atoms like metal nanoparticles, or how we fine-tune the way in which defects are created and their shape and so on. So this is the way to fine-tune this material. So here we can see in detail the mechanism proposed, and then how effectively, carbon dioxide is absorbed in the surface, and then hydrogen in the nanoparticle, and so on and so on. So for the reaction of methanol production, and also the carbon monoxide, which is the competing reaction. Now, hydroamination, as you can see here in the title of the slide, is the addition of hydrogen and amine across a double or triple bond. And this reaction is atom efficient. It's not so studied as carbon-carbon coupling reactions, which are well known by famous reactions such as Sonogasira and Heck, both of them crowned with Nobel Prizes, or at least Heck's for sure. I don't know if there is a Nobel Prize for carbon nitrogen bond making, probably not. So this is a good point to further research. But the important thing to take into account here is that nitrogen has a lone electron pair, and this is not willing to interact with a double or triple bond because of electronic repulsion. Therefore, this reaction without catalyst should have a very high activation barrier, and that is the role of the catalyst that we are going to study. So here, just summarize early studies with homogeneous catalysts based initially on lanthanides, and then they can bind the double bond, since metals are electrophiles, and this delta plus is interacting well with the carbon-carbon double bond. Now, two ways that we can see how this is the interaction, just highlighting from the literature in the left and in the right. In the left, metal, remember the delta plus is attracting the carbon-carbon double bond here in the left one, you can see. But then in the right one, what we see is the opposite, is that metal, delta plus, is attracting the nitrogen, and in the left part of this right diagram, you can see the metal double bond nitrogen. So in this case, let's say nitrogen from the amine, from the reactant, has displaced the double bond, or the carbon-carbon double bond, in the interaction with metal. So there is a competition who is taking the metal, either the carbon-carbon double or triple bond, or the lone pair of nitrogen. This is an important viewpoint to take into account how this reaction operates. Now we are using a cluster instead of periodic DFT, but then the cluster was carefully obtained from the mxene, so that we have a good balance between titanium coordination and oxidation states that you can see here. Titaniums, all of them would be 3 or 4 plus. And then the terminations, we selected a few of each of the more widely known, hydroxide, fluoride, and oxygen. So with this cluster and using B3LIP as functional, then DEF2 single valence polarization as basis set, we are carrying out the study, which I show you overall view of the mechanism. So I'm not going to show step by step. I think this is more instructive to show you the overall view. This is, sorry, anti-clockwise, probably not the standard, but then we start by the right part in which the active site is formed, and this is interaction of titanium with the amine, as I showed you before in the literature survey, the one in the right. So this is the nitrogen of the amine has interacted with one of the titanium in the cluster, and then the alkene is interacting now with this active site, and then already making in the first step the carbon-nitrogen bond, which is typical of hydroamination. And then afterwards, after this catalyst containing one molecule of amine is formed, then the second molecule of amine is coming, and this second molecule will be the next active site, whilst the first amine molecule will be the product of the reaction. Okay, so both of these amines are here bonded to the same titanium atom, and these two hydrogens that you can see in the left part in red, these two hydrogens of the amine will be given in two different steps: first proton transfer, second proton transfer to the right part of this square 4-atom intermediate, to give these two hydrogen atoms to either side of the carbon-carbon double bond and to the nitrogen to give the product. So now the same we can see in a more accurate way. So we can see that in the step 2, okay, the nitrogen here chemically is bonded to two titanium atoms, not only one as in the scheme, but then these are large distances, as we will see in a minute, which means not too strong interaction, which is good for catalysis. Then in the number 3 intermediate, I highlight that the titanium is interacting with two molecules of amines, okay, initially, and then the hydrogen of the second amine is in good position to transfer to the double bond, as you can see there. So that in the step 4, also you can see now that I highlight with red arrows that two titanium now are interacting with the either amine molecule, and then in the right amine molecule, now the second hydrogen is ready to be transferred to the product of the reaction, which will be dissolved. Okay, so I just give you a hint of some of the interesting bond distances. So in intermediate 2, for instance, you can see that titanium nitrogen bonds are larger than 2.1, so which is interesting, because that means that the amine is not too tightly bound to the catalyst, which is good. And then also there is the importance of the fact that in mxenes, titanium atoms are relatively close, so that the second titanium atom, as we see in the transition state 2 and in the subsequent intermediate 4, are taking part in the reaction and stabilizing either of the molecules. On the left part of 4 would be the product of the reaction once this second hydrogen is transferred. And then by losing these two hydrogen atoms, the amine in the right part becomes the new active site, okay? So this is a kind of transposition. The first active site is making the catalyst, and this first amine molecule will be the product of the reaction, while the second amine will renew the catalytic active site. Okay, so this in 3D is not easy to see because of so many atoms, and the perspective is as good as I can, but this is just to, if one wants to check more carefully how are the reaction in 3 dimension. Okay, so that is about the mechanism of the reaction. And so in the second part of the talk, we were studying in a completely different study, and this is in collaboration with South Korea, the work of the group of Subong Hong, amination, methylamination, methanol amination in zeolites, which is the reaction that you can see in the top part of the slide, which is not a hydroamination, but when we study the mechanism, one of the intermediate states happens to be a hydroamination, and then it is important or interesting to reflect on how these two different materials catalyze a hydroamination. So as you can see from this old review, actually old review, and then in a sense, amination, methylamination in zeolite has been overlooked for many years, although it is in an reaction with industrial importance because of the interest of monomethylamine and dimethylamine, specifically in some industrial chemistries. Okay, so I think the second family of materials are perhaps some more widely known, but still is important for those of you who are not familiar to just make a very brief introduction. So in the left, you can see tetrahedra of silicon or aluminum, and then oxygens in red by sharing corners, then the dimers, and then polymerize, silica polymerization reaction, silica and alumina polymerization reaction, and then the oxygen bridge, and you can see several examples. Particularly when aluminium enters in this compound, then this, let's say, formally negative charge can be compensated by cations such as sodium, but then when the cation is hydrogen, this goes covalently bonded to the bridging oxygen, making a Bronsted site, which is crucial for catalysis. And then further condensation of monomers or dimers gives place to these micropores or cavities, which is one of the peculiarities of zeolites, that they are not only crystalline materials, but also they are microporous. And a considerable difference with mxenes that only had one structure. Zeolites have more than 200 structures, and the number is growing. And hence obtaining new zeolites is always a good thing in order to find possible new materials that could be good for not only catalysis, also for separation and other applications. So here I highlight some of the early work in synthesis of zeolites. The Barrer introduced organic molecules, and then in the mid-90s, important computational work. Some of the authors are in the audience. And since then, there is a lot of work in zeolites. Now, proposed mechanism for this amination in zeolites, you can see from the literature 4 possibilities. The two on the top refer to ammonia being absorbed in the Bronsted site and then becoming an ammonium cation. And then in the left, this ammonium cation transfer a proton to the methanol molecule, becoming protonated methanol. Protonated methanol lose one water molecule and makes a bond with the methoxy, and with the methyl group, and they absorb ammonia, making the product of the reaction. Okay, so then the other one in the right, top right, is a slightly more complex mechanism, in which protonated methanol is attacked by a molecule of amine, not absorbed as an ammonium, but on the other hand, interacting with this methanol, interacting with ammonia. And then the other two proposed mechanisms are based on absorption on the Bronsted side of methanol instead of ammonia. So being ammonia more basic, it's probably, I like to think that the two mechanisms on the top seem more likely, but the 4 of them have been proposed. And I'm sorry that I don't know why this is not properly shown, but this is not published, and I just wanted to give you a brief idea, but not so brief. I'm very sorry about this. But what I want to highlight here is that normally the mechanism proposed depends on the number of active sites, so number of Bronsted sites. So in this study, when we increase the number of acid sites, so from the left to the right, the conversion of the reaction does not drop, and therefore with, and also even the selectivity to monomethylamine increases when the number of Bronsted is the smallest. And therefore, we thought that something else apart from the mechanism based on Bronsted sites is at play. So in analogy, I'm so sorry. In analogy to methanol to olefin reaction, because methanol is one of the reactants and is the reactant that is in excess, we propose that similar intermediates are formed. And this in particular refers to one of the important intermediates in this reaction is a cyclohexadiene methylene derivative. Okay, we can see here in the intermediate one, this is one of the intermediates proposed in the methanol to olefins reactions that we propose. It's also present here, and this has been detected by mass spectrometry in the experiments in the group of Suk-Bong Hong in South Korea. So we start with this. This is an important intermediate, neutral intermediate. So in the step 2, in the intermediate 2, we propose that this is interacting with simultaneously one molecule of ammonia and one molecule of ammonium. Ammonium is produced through protonation from the Bronsted site. And therefore, as I told you in the introduction, ammonia with the lone pair of nitrogen will never react with the double bond that you see there, unless there is something that is depleting electronic charge from this double bond. So in the previous hydroamination example, this was the metal, the transition metal. And then in this case, we propose that ammonium cation is able to protonate this double bond, as you can see in the transition state 1, and as you can see in the intermediate 3. And now, although the activation barrier is high, so 132 kilojoules, this is the best that we have found. And this allows the ammonia molecule to add to the terminal carbon-carbon double bond and produce this positively charged intermediate, which now with much less activation barrier is able to interact with the nearby ammonia molecule and then make another ammonium cation, while the molecule remaining is not positive, because now it's ended by NH2. So this is a primary amine that is one stable intermediate, and for this second transition state, the activation barrier is extremely low. So the difficult part is the rate determining step is step between 1 and 2, so the transition state 1. And this is the first part of the reaction, which is the insertion of the amine in the carbon-carbon double bond of the so-called hydrocarbon pool, as it is called in the methanol to olefins. This is in 3 dimensions. But now let's go to the second part, which is the elimination of methylamine. So starting in the upper left, from intermediate 5, now the direct interaction with methanol of this intermediate was not possible. The activation barrier was extremely large. So what we consider, so if we go right, is the interaction not with the methanol, but with the adsorbed methoxy, which is well known also in zeolites as being an active site for many catalytic reactions. And this is formed by interaction of methanol with the Bronsted site. So then what we found is that with only about 60 kilojoules per mole, this methyl group can insert into the primary amine. So then this is giving another positively charged molecule. Now it contains, let's say, we localize the positive charge in the ammonium, in the nitrogen atom. And now what happens is that the way for this molecule to release this positive charge is precisely through the unstable hydrogen that was inserted in the first part of the reaction, that is close to the not aromatic ring, but in the cyclo in the cyclohexadiene, okay? And now this hydrogen is transferred or donated as a proton to a amine molecule, which becomes an ammonium cation, as we can see in the TH4 transition state 4, with 90 or 91 kilojoules per mole as activation barrier. And this gives, again, let's say the catalyst or this active molecule, the hydrocarbon pool molecule, restored, whilst now what happens is that this molecule suffers, the molecule is just losing in order to become the hydrocarbon pool, really is releasing the product of the reaction. So if you see in TH4, the CH3NH2 is separated. So this gives the reaction product, which is the methylamine. And then at the same time, the hydrocarbon pool is restored. Okay, so that is the full mechanism of hydroamination, certainly different to what we found in the other material without the participation of a transition metal in this case. And this is one way, our suggestion to explain the experimental results, taking into account that these hydrocarbon pool molecules have been detected in the experiments through mass spectrometry. And this was not proposed before, okay? The fact that amination in methanol amination for methanol amination in zeolites, something related to the hydrocarbon pool mechanism had not been proposed. So this is our main suggestion on this work. Okay, so now just to show you handwritten how difficult it is to find transition state and reaction paths. And here there are some of the possibilities that did not work. Okay, so for instance, you can see in one of the possibilities is interaction of ammonium cation with the carbon-carbon double bond without the participation of the amine, and this is not working. This is giving a very high activation barrier. And so on, for instance, what I call reaction 10 below the one in the left. So it is, again, this is an interaction of, direct interaction of ammonia molecule with the carbon ring on the one hand, and interacting with the CH2 part of the intermediate, and this is again giving a very high activation barrier, and so on and so on. So we tried not only to find a mechanism which, in spite of having 130 kilojoules per mole as activation barrier, we think it makes more or less chemical sense, but then we also try to see that many other possibilities are not possible, so that this also gives more strength to our proposal. So before wrapping up, I would like to just two reflections. One of them is we are hoping that in the next future, new algorithms, either or not with use of artificial intelligence, will be able to somehow make a fully automated way to make reaction mechanisms. Okay, this is something desired. It would be a dream, and it's something of quite much need in order to explore all possibilities. Catalysis is, you know, much better than me. It is a very complex phenomena, and automating this would be something that could be possible in the coming years. So that if this is the case, I will be one of the last persons to show this handwritten way of considering mechanisms by hand. Okay, so the second final comment is that we took into account in both of these studies experiments that I didn't focus, just to show you more detail of the mechanism. So my idea was try to introduce you this reaction so that you can understand from a kind of introductory point of view, but experiments were also taken into account. Now, thank you to the team and the computational facilities for funding, and especially thank you for your attention.
Nicely to time. Thank you for that. Do we have questions? If you have a question, please wait for the microphone, particularly so Chairman can hear you. I think Corinne has the microphone.
Thank you. It's Graham Hutchings from Cardiff. So I was really interested in both parts of the talk, and I've got a question on the second part. If it's the hydrocarbon pool mechanism, which I can go with because that seems to be the way in which methanol will react over a zeolite, there will be an induction period. It might be difficult to see it because it's very fast chemistry, but in terms of the methanol to olefins reaction, there was an induction period. So do you see an induction period experimentally to back up that?
Yes, there is an induction period. The problem is that in this slide, so I don't know if you can see better now.
Yeah, my eyesight's not that good, so.
Okay, well, so I think there is an induction period, but I cannot give you details about it here.
No, okay, because there would have to be an induction period.
Yeah,
it's just, it's fascinating. Can I ask a second small question? Okay, that other people on the first part. The superconductivity in those materials is very interesting, but obviously it's very low temperature. Is there any variation in the onset temperature for superconductivity with the variation in the metal cation that's in there?
With the variation in?
Yeah, in the metal, the M.
Oh, yes. I think let's have a look. Okay, so so actually, one of the cases that we see in the slide, in part D, okay, there is the terminate. All these cases contain surface termination. The effect here is mainly due to the termination. But then, for instance, if we have a look to the second graph, one of the compositions contains this square, which means no termination. Actually, this could be the bare mxene, and therefore this is the case in which metals of different layers are in contact. And this is an important case here with no superconductivity is observed. And then here it is basically showing niobium and also titanium. So I don't have the data for titanium, but I think there is also a big effect of the metal. So since metals, apart from the termination, are the atoms more close to the surface, and the ones that give the conductivity properties to the material. So it's not due to the carbide or nitride layers. Is mainly due to these metal layers. And so yes, I think I don't know in which extent, but there is a positive effect of type of metal.
That's interesting. It gives scope for that, I think. So
yeah,
it's good. Thank you.
Hello, my name is Keith Simons. I'm an independent researcher. In the past, I've collaborated on looking at electrochemical reduction of carbon dioxide to C2 and C3 paraffins. You needed very well-structured catalysts to perform that. I was just wondering, given the conductivity of these materials, the mxenes, could you perform electrocatalytic reduction of carbon dioxide and do carbon-carbon bond formation?
Okay, well, from there are many studies of involving mxenes and redox catalytic processes due to the electric conductivity of these materials. They have been tested, and there are studies of electroreduction of carbon dioxide. So I cannot tell you now which type of mxenes or which chemical compositions, but in fact, the property of conductivity has been explored and is being heavily explored for electrocatalysis. Yes, definitely. Yeah.
We have time for one more quick question, which I'm afraid is
Thanks. Thanks for a really good talk. It's David Willock from Cardiff again. So you said a few times that the barrier for your process using a carbon pool is quite high with 132 kilojoules. Are there any other molecules in the carbon pool with a double bond that's less sterically hindered that might help with the barrier?
I didn't find, but let me show you if now we can see better from this. No other molecule that I found in the hydrocarbon pool mechanism in the left contains this bond.
You've chosen a double bond with a CH2
terminal double bond. Yeah, terminal double bond. This is let's say the best candidate, since other molecules containing double bonds are not accessible, since they normally have methyl groups attached. And so that is the only molecule we found that could do the job.
Great. Okay, thanks.
okay. I think in the interest of time, we should move on. So let's thank German again.
Thank you so much.